This conference will now be recorded.
All right, this is some videos of extra notes that I promised you guys, starting with section 2.6. I left my packet at home, so I had to try to do from memory which ones we had left open. I could not remember which one of these it was, or if both of them were left open, so I'm going to start right here. We're supposed to take two derivatives of this and then take 1/2 and evaluate it. I would start this one off by writing it as 6t plus 1 to the 1/2. And then we're using the power and chain rule for that first derivative. So that would be a 1/2 and then 6t plus 1 to the negative 1/2. But then we have to times it by the derivative on the inside, which is 6. So that's actually 3 times 6t plus 1 to the negative 1/2. Okay, then we want to take the second derivative. We don't even care about moving that guy to the bottom because we're going to take another derivative. So we bring the negative 1/2 to the front and times it by the 3, so that's negative 3/2. And then 6t plus 1 again. We subtract another power, so that's going to be negative 3/2 now. And then this is going to be again chained by the derivative of the inside. So when we multiply that together, that's negative 18 divided by 2, so that's negative 9. And I'm actually going to move it to the bottom now since this is the derivative I was looking for. So that's 6t plus 1 to the 3/2. Now we're supposed to put in a 1/2 for the evaluation of this. So this is going to be negative 9 over 6 times 1/2 plus 1. And then remember, this is a square root that is then cubed because that's what 3/2 means. So we need to work out the inside first. That's going to be a 3 plus 1, so that's a 4. And I'm going to go ahead and convert this to a radical. So that's square root of 4 and then cubed. So that's negative 9 over 2 cubed, or negative 9 over 8. And again, I think we might have done this one in class, but just to be safe, I'm doing it here. And then let's make sure we do the following one as well. The sorry. Sometimes this PDF stuff does not want to go up and down the page correctly. So let's do this one again as well, in case we already did it in class. We're taking a triple derivative of f and then plugging in 0. I would not use the product rule here if you don't have to, because this can be distributed pretty easily. So that's 4x to the 5th minus 16x to the 4th plus 12x cubed. So if we take the first derivative of that, that would be 20x to the 4th minus 64x to the 3rd plus 36x squared. The second derivative would be 80x to the 3rd minus, that will be 12, carry the 1/18, 192x squared plus 72x. And then the third derivative would be 240x squared minus, that's going to be 384, I believe, x plus 72. And notice we're plugging in 0 for all the x's, so essentially the answer just ends up being 72. And again, I think we might have done both of these in class. I just wanted to make sure we covered our bases. So then the next thing was section 2.7, the implicit derivative. So this is when you're taking a derivative with respect to a certain variable, but your equation may not be easily solved for y. So you may have to take derivatives of both x and y at the same time. And we learned that if you're ever taking a derivative of a piece that is not the variable you're taking with respect to, you chain on a d variable, dx, or whatever your respect variable is. So I'm going to do this product rule one here. There's quite a bit going on. So for this piece right here, you kind of have to do the product rule. So it's the first function and the derivative of that function, the second function and its derivative, which because it is a y instead of an x, we chain on a dy dx. So this piece right here is going to be in a parentheses. I'm going to write it. That would be y squared when we multiply the first diagonal plus x times 2y would be 2xy if you write it alphabetically. And then we have our dy dx. on that. And then we're going to do the same thing here. If we think of this as being 2x and this as being y, sorry, backwards. Let me back that one last up. Put our second equation down. Then the derivative of 2x is 2. The derivative of y would be 1, but it's a dy dx since it's the wrong variable. So 1 dy dx. Okay, so then we have our derivative of the second piece. Give my computer just a second. There we go. Would be 2 times y, and then 2x times 1, so that's just going to be 2x, and then dy dx on that one. The derivative of 10 is just 0. So we want to move anything that doesn't have dy dx to the other side, and we're going to keep the ones that do have dy dx over here. And I'm going to go ahead and get to a point where I go ahead and pre-factor that out. So if we leave the dy dx's on this side, you'll get a 2xy plus a 2x that are both left over with a dy dx times both of them. So I kind of pre-factored that out. On the other side, you subtracted over a y squared and a minus 2y. So to finish this off, we solve by dividing by this parentheses. So the formula for my slope of my tangent line is going to be negative y squared minus 2y all over 2xy plus 2x. So there is dy dx. Okay, let's look at number 4. This one is at least no product rules because that's a plus between them. So the derivative of 2x, or x squared, is just 2x. The derivative of y squared is 2y dy dx. And the derivative of 16 is just 0. So then we subtract over our 2x to get the dy dx on one side by itself. Excuse me. And then we divide both sides by 2y. So that's going to be negative 2x divided by 2y, and you can reduce that. So that's going to be dy dx equals negative x over y. So there's my formula for the slope of my tangent line. I believe we did 5 in class and 6, so that leaves us with number 7. So we're taking the derivative of this so that we can find the slope of the graph at a specific point. So we're going to do our power rule on each of these. So the derivative of x to the 2/3 is 2/3 x to the losing a power, so that'd be negative 1/3 if we subtract 3 over 3, plus 2/3 y to the negative 1/3, but because this is y and not x, we tack on our dy dx. And we get equals to 0 because the derivative of 5 is 0. We're going to subtract the, and I'm not worried about the negative exponents just yet. I'll get to that in a second. But we're going to subtract that first 2/3 over because it is not got a dy dx. So negative 2/3 x to the negative 1/3. We can multiply both sides by 3 over 2 to get rid of the fraction. On this side, it completely cancels out. On this side, it also cancels, but you still have a negative 1 because this was a negative fraction. So I have y to the negative 1/3 dy dx equals negative x to the negative 1/3. We would divide both sides by y to the negative 1/3. So this gives me dy dx equals negative x to the negative 1/3 over y to the negative 1/3. Now this is where I'm fixing my negative exponents. Since they're both negative, they both need to flip-flop. So this is actually dy dx. The negative right here doesn't have anything to do with the exponent, so it's still negative, but it's going to be y to the 1/3 over x to the 1/3. Now we need to actually find the slope here by plugging in x is 8 and y is 1. So this is negative. Remember, a 1/3 is a cubed root. So negative cubed root of 1 over cubed root of 8, which is negative 1/2. So there's the slope of my tangent line. I believe we did 8 and 9 both in class. So that moves us on to number 10. This is just wanting us to show that we can take the derivative implicitly of an equation, but we can also look at it as what if we had solved it for y and do the results end up being equivalent. So if we take this implicitly, that means that we're taking the derivative of each part individually. So here's the implicit part. And that's when we get the dy dx's. So we're going to take the derivative of x, which is 1. Derivative of y squared would be 2y dy dx. And then derivative of 1 is 0. Derivative of 0 is 0. In just a second, my pen likes to freeze. There we go. So equals 0. And then I would solve this for dy dx by subtracting the 1 over. And then dividing by negative 2y. So dy dx is a negative divided by a negative, so that's a positive, so it's going to be 1 over 2y. And what you have to remember is that this is the formula for the slope of the tangent line, and notice it has a y in it because we had to do it implicitly. If we had solved this for y to begin with so that it looked like a normal function, we would have had to subtract or I would have just added I would have just added the y squared over. And then I could take the square root to get rid of that. But the problem is when you take a square root, you get plus or minus in front of it. So you have to distinguish, is this the top half of the graph or the bottom half of the graph? And so really you have two parts here, and we're going to take the derivative. So if you're doing, if your y's are greater than 0, or yeah, greater than 0, not greater than or equal to, then we would be using the top half of the graph. So we would be using y equals, and I'm going to write it as a 1/2 now. So it'd be x minus 1 to the 1/2. If we had the bottom half, y is less than 0, so down here, we would be using y equals negative x minus 1 to the 1/2. So the derivatives of these would be different depending on which part of the graph we're on, because this is technically not a function. So you do have to distinguish which part is which. So this would be 1/2 x minus 1 to the negative 1/2. And this one would be y prime equals negative 1/2 x minus 1 to the negative 1/2. So both times you could tack on the chain rule, but it's a 1 in both cases because derivative of x is 1, so it's not completely necessary there. But so this next question, so the formulas look different right now, but that's because this is an implicit one, which means it can have x's and y's in it, and this is how to represent the derivative if you just have the x. So this says use the graph to estimate the slope of the tangent line at the labeled point. You can kind of count here if you want, but I'm going to verify the result analytically by evaluating dy dx at that point. So the point here that they're focusing on is 2, negative 1. So if we plug that into here to dy dx, we only are plugging in the y value because that's all this formula needed because the x ended up not being part of it. So that's 1 over 2 times negative 1, which gives me a slope of negative 1/2. You can see that if we plug it into the y prime this case, because it is the bottom half of that graph, we're plugging in x this time, which is 2. And that would be negative 1/2. And that's a 1 to a negative 1/2 power. So that means we need to move that to the bottom. So negative 1 over 2 times the square root of 1, because once it moves to the bottom, it would be a positive radical. So that's just going to be negative 1/2 again. So you do still get the same slope. So that's all we were trying to verify here, is that this process can work both ways to get your slope of your tangent line. All right, so that leads us into section 2.8, the related rates. I skipped a couple of the word problems because we were running short on time. I don't believe I did number 3 as well, so let's look at this guy. If I take the derivative implicitly with respect to time, remember we're going to be getting dt's for anything that's not a variable t, so pretty much everything. So we get a 2x and then times a dx dt plus a 2y times dx dt, and then the derivative of 25 is 0. X is 4, so we're going to have 2 times 4. We don't know dx dt, it's the part we're looking for, so that's going to stay that. The y is a 3 from reading my directions. This is supposed to be dy dt. Sorry, I wrote that incorrectly. And dy dt is -2. So this is -12, and that's 8. So 8 dx dt Sorry, my internet has been super slow today, so it's causing problems with my pen lagging. Give it a second. All right, so dx dt, and then this we said was -12. Now to solve this, we want to, of course, move the 12 over. So that would be 8 dx dt equals 12. So it would add over. And we divide by 8. So 12 divided by 8. That is going to reduce by 4, so that's going to be 3/2. So there is dx dt. All right, we did number 4 in class, so we're going to look at 5. This is saying all edges of a cube are expanding at a rate of 6 centimeters per second. So that's the change in the side length. How fast is the volume of the cube changing when each edge is 2 centimeters? So to know this, you have to know what the volume of a cube is. The volume of a cube is the 3 sides multiplied together. So it's s cubed, because a cube is 6 different squares. So when we look at this, we're thinking this is the formula we're dealing with. So I know that the sides are changing at a rate of 6 centimeters per second. So that means that this 6 is my ds dt, change in side length over time. I'm looking for d volume dt, because I want to know how fast is the volume changing over time. And I know that the side lengths were 2 centimeters. So we're going to take this derivative implicitly with respect to time. So derivative of v is just a 1, but because that's not a t, we have to tack on dv dt. Derivative of s cubed would be 3s squared, but we have to tack on ds dt here because it's not a t as well. Okay, so then we plug in what we know. So we don't know dv dt, and timesing it by 1 doesn't really change anything. So this is what we're solving for. We know s is 2, so that's 3 times 2 squared. ds dt is 6. So we just need to work out the right side. So this is 3 times 4, so that's 12. And then times 6. Sorry, my pen is really struggling. So this is 72. Now, what we have to do is figure out our units. It's centimeters per second for side length, but remember there are 3 sides being multiplied together. So this is going to be volume. So it's centimeters cubed per second. So that is how big the volume is changing per second. All right, I'm going to end this as the end of part 1 just so I can try to see what's going on with my internet, and then I'll come back and record the second half of what I wanted to do, because that way I can make sure you guys at least get one good video.